Alright, here is FRQ number 4. So part A wants to know what is the equilibrium length of the spring and how do I know? So, these. Okay, so we want to use this graph that it gives us, and as you can see here, this is the PE line that it has given us. So we can see that there is no PE, or PE is 0, at length of 20 centimeters. Now, this tells us that that is our equilibrium length, because when it's at equilibrium, there's no PE. Since PE is 0, that is implying that the string is not stretched or compressed, so that is why it is our equilibrium length. So, equilibrium is at 20 centimeters or 0.2 meters, because PE equals 0, meaning the spring is not stretched. Is that even how you spell stretched? I don't know, stretched or compressed. Okay, moving on to part B. Okay. If the block's turning points are 14 and 26, draw a line that indicates the total energy. And we need to copy the graph, so let's do that first. This is energy in joules. This is X in centimeter. Okay, and then we need to draw PE. Copy it as best as we can. Okay, so there we have the graph that was given to us. So now we need to draw a line on the graph that indicates total energy. Okay, so we know that the turning points are here at 14 and then here at 26. So we know that that is where energy is going to be, essentially, that's where that's as far as they go, or that's how far the string is stretched. So you know energy can only go, it can't get any more from there. So what we need to do is draw our line where 14 and 26 hit the curb. I'm gonna redraw mine. So I'm noticing mine's a little wider than that might be a little better. So we want to draw our line. Fix this side. Draw. So that is the line that indicates total energy at because they are at those turning points. Okay, so on to part C. On the same graph, draw the KE graph, and it must be accurate. Okay. So I'm gonna put C right here. Okay, so what we know is that this is as much total energy there's gonna be. So that means our KE can't exceed that. Especially since the top of the parabola is gonna be at 20. And we have to remember that there is no PE at 20. So that means it's only going to be KE. And so since this line indicates, write it, total energy, since there's no PE at 20, that means all the total energy is going to be in KE. So that means our parabola is going to look a little something like this. And then our PE is at max at these turning points, so that means our KE is at the lowest point. So let's go ahead and write KE to indicate that that parabola is for KE. Alright, so on to part D. It wants us to calculate the spring constant. So for this, we want to go ahead and set up energy because that is what is given to us. So PE spring equals 1/2 kx squared. So now what we need to do is we need to find a point on the graph and best match it to an energy as close as we can, and we're going to use this graph just because it's a little more accurate and precise compared to mine. So let's go ahead and estimate a spot. Let's use 12. Okay, so as you can see, I kind of just drew to estimate about when it's at 12 centimeters how much energy it has. So I'm going to estimate this to be, it's kind of between 10 and 15, so about 12.5. So now I can use that as my PE spring. So 12.5 is equal to 1/2 K. And now I'm not gonna use 12 or 0.12 because I need to use the distance from here to here. So then in that case, that would be 8 centimeters or 0.08 meters squared. So to explain that again, rather than using 12 centimeters or 0.12 meters, I'm using the distance from equilibrium. So I would take the equilibrium and subtract, and then I just converted it to meters. So now we can go ahead and plug that into the calculator. Okay. And then we're solving for K, so and then the units for the K constant is newtons per meter, and that equals K. Okay. So now moving on to part E. Okay, so what we can do is we can use the graph to help us find KE max. So we have to remember that we drew our max line for total energy. So that means our KE max isn't going to be anywhere up here. So KE max is also when PE is 0. So we want to look here at 20. Excuse me. So we want to look here at 20 and then kind of estimate where that line is. And it's like a 6.5. So we can write it out. Okay, and then remember at KE max, there is no PE. So KE max equals ME. And we can estimate KE max to be about 6 joules. Okay, now on to part F. It wants us to determine the block's kinetic energy at 16. So we can set up energy. So we can set up energy. So PE plus KE equals ME. So we can go ahead and put 1/2 x squared and then plus KE because that's what we're looking for, and we know total energy is about 6. So now we can go ahead and just solve for this using the K constant we found. You could probably also use the graph to estimate about how much it's going to be. So for our x, we're kind of doing the same thing. So it wants it at 16, but we want the in between, so it'd be 20 minus 16, which is 0.04, but then that's in centimeters, so it'd be 0.04 meters. Okay, so let's go ahead and solve. We want to go ahead and isolate for KE. Okay, so we found KE at 16 centimeters. And for this problem, these numbers are all kind of estimations because on the graph, it doesn't give us anything explicit. There's no lines drawn for us to explicitly show like where the curve is hitting. So most of these are estimations. You could get different answers by, you know, how you interpret the graph. You know, it could be a couple decimals off, but it's okay. Okay, on to part G. Grab another piece of paper. Okay, so part G, final part. Okay, what will the turning points be if the total energy is doubled? Okay, so that means, so we found that total energy was about 6. So double that, you get 12. So the total equals 12 joules. Okay, so what we can do is set up energy. So we're solving for x squared, and we are going to use the 12 joules. Okay, so calculator. Okay, so you get 0.78, and so this is actually the distance from equilibrium. So that's right, because that's what we have been doing. We've been plugging in x as the distance from equilibrium. So this is also the distance from equilibrium. And what that means is we remember our equilibrium is 20 or 0.2. So what that means is we need to add and subtract. Okay, so I'm gonna write that this is 8 centimeters. I'm gonna do it in both meters and centimeters just because our graph is in centimeters but SI units is meters. So just go ahead and subtract 20 minus 7.8 for our first turning point, and that is 12.2 centimeters. And so then you would divide that and get 0.122 meters. And then we can go ahead and add 0.78 to get our second turning point. And again, divide that 0.278 and convert it to meters. And that those are our new turning points. And again, that's because we found the new distance from equilibrium. And so you want to find it. You want to find the distance on both sides. So you would have to add it and subtract it. And that concludes FRQ number 4.